Okay, this is the second part of section 24.1. And although chapter 24 deals with magnetism, what it really deals with is a link between electricity and magnetism. That link between electricity and magnetism is so important. It's what actually allows our entire society to function. The computer you're watching this on depends upon that link between electricity and magnetism. The light bulbs that are running in your house and your room, the fan that's on, what comes out of your outlet. Everything that we do that makes our life convenient has to do with that link between electricity and magnetism. In 1820, a scientist by the name of Hans Christian Ørsted, and he actually, if I understand it right, was effectively at that time a high school teacher, was demonstrating to his students what they believed was, what he believed, that there was not a connection between electricity and magnetism. He took a compass and he laid a wire across the compass and hooked that up. Now, at the time, he didn't really have a battery. He had a Leyden jar, he had a capacitor. But he hooked this up so that the electricity ran, let's just say the electricity ran this direction. I'll have to do that. And this compass needle turned that direction. In other words, the electricity caused there to be a magnetic field because electricity was flowing and this magnetic field caused the compass to turn. More important, the magnetic field was perpendicular to the flow of electricity. This was the beginning of the modern era. Once we understand this, we can start making it practical. So the very first thing you need to understand, what Hans Christian Ørsted established, is there is a link, a connection between electricity and magnetism. And basically, an electric, electricity produces a magnetic field. Because what would cause the magnet to move would be a magnetic field. Now, it turns out that there are three links between electricity and magnetism, and the first, they're called the three right-hand rules that allow us to see that link. So let me show those to you, and I also have a video that I want you to watch that shows this with demonstrations that I can't really show you at home. What Ørsted discovered was that this wire caused there to be a perpendicular magnetic field around the wire. And if you look at this, I've got a circle here. That circle is theoretically perpendicular at every point to the wire. So it's perpendicular here, it's perpendicular here, it's perpendicular here, it's perpendicular here. I haven't drawn a real good circle, but you get the idea. And there's one right below it, and the same thing, perpendicular around there. If I hold it up this way, that magnetic field is perpendicular around. And this is how we determine what the magnetic field looks like. In other words, if I was to put a magnet, a compass here, the compass would follow that magnetic field around. So if I put a compass here, I guess it would be this direction. The magnetic field would be pointing this way. If I put it here, it would be pointing this way, and here it would be this way. One of the things they discovered, Ørsted did, was that if you took that compass and you put the wire on top, it turned it one direction. If you put the wire underneath, the compass turned the opposite direction because of this principle. So here is what is called the first right-hand rule. By the way, a lot of old books will call these the left-hand rules because physicists used to talk about electricity flowing from negative to or positive to negative, but actually electricity flows from negative to positive, and so these are now called right-hand rules. The first right-hand rule says is this: we take a wire, a current-carrying wire, you grab it with your right hand, and you grasp that wire with your thumb in the direction of current flow, and your fingers will represent the magnetic field. So I don't know if you can see that. If the current is flowing this way, this curve, my fingers are following that magnetic field. If you were to turn the electricity and have it go the opposite direction, what's going to happen now is that my thumb is pointing toward me, and my fingertips are actually going the opposite direction, if you can see that, of the magnetic field represented by this. And so when we think of a wire, well, here's the first-hand rule. First right-hand rule says grasp the wire, obviously with the right hand. Thumb in the direction of current flow. That means toward the positive. And your fingertips, or fingers, I shouldn't say fingertips, represent the magnetic field. Okay, now, if I was to take a wire, then this is positive, and I were to grasp that with my fingers, what would happen is the magnetic field would be a circular magnetic field around that. If I was to turn that wire upside down, put positive down here, now my hand would have to go this way, and now this would come like that. And it would be the opposite direction. This is going underneath. So this one, the field is actually this direction. This is the opposite way. It's really hard to see that without actually having a wire. I just took a dowel, grab it, fingertips go that way, turn it around, your fingertips go the opposite direction. Now, there's another way to draw this, and that is that dot represents a wire where the current is flowing out of the board. And if I do this, that's a wire where the current is flowing into the board. If the wire current is flowing out of the board, this would have a magnetic field around it that would look like this. And this one would have a magnetic field around it that looks like that. The idea behind this is that this is like an arrow that's coming towards you, and you would see the tip of the arrow. This is the feathers at the arrow if I shot an arrow away from you. This is what you would see. That is our first right-hand rule. Now, the first one's kind of interesting, but it's not super practical. It doesn't do much for me except tell me there's a magnetic field. So let me, I should have left that one up there, but that's okay. Let me move on to something which is kind of more interesting. And that is that if I was to take a wire and I was to make a coil out of it, something very interesting happens. If you look, both of these around that coil, let me bend that a little bit more like this. The current would be flowing this direction. But watch what happens if I move this one to the other side. I don't know if you can see that or not. It's actually fairly difficult to picture. But these two now are actually heading, the magnetic fields are in the opposite direction. Look at the one on my right, your left. It is going down. The other one is going up. All right, those are opposite directions. So it's kind of interesting that would happen. Same electrical, but we have those heading in opposite directions. Actually, something is not right here. They should be. They should be going in the same direction. Do I have these backwards? Oh. Oh man, I have this upside down. I'm sorry. This should be like this. I had those on backwards. They actually should both now be heading both down. I don't know if you can see that or not, but this is heading down and this one is heading down. When we take a coil of wire, and let me, if you think of this, think about threading a shoelace. If I was to take, say, this wire here, and I was to picture what's happening, on one side it's coming out of the board, on the other side it's going in. Electricity, say, is coming out and then going back in. And if we do that, this would represent a coil of wire with electricity coming out and then circling back in. If we had it like this, it's coming out and then it's going back in the board and then coming out and going back in and so on. Well, watch what happens. If I take and put my magnetic fields around these, here, these are pointing up, but the same thing here. If I do this, this magnetic field, if I trace it around, is coming up as well. So let me clean that up just a little bit. If I have my coil of wire, what we're going to have through the center of the wire is that all of the magnetic fields will be pointed in the same direction. And in fact, this would be north-seeking and this would be south-seeking. This would be the north end. In other words, if I was to put a compass right here, let's say the compass is pointing this direction, and I turned the electricity on, this would line up this direction, and down here it would line up this direction. In other words, it becomes what we would call an electromagnet. Now, let me show you an electromagnet. I have, forgot to plug it in, sorry about that. I have my power source. This is like a big battery. You could do this with a 9-volt battery. I have a nail, and I wrapped a wire around that nail in a loop. And if I take and turn this on, there's now, I don't know if you can see it, but 5 volts across. And all of a sudden this nail becomes an electromagnet. Right? If I take this off, those fall off. It's temporary magnet right now. But without that on, by the way, I have magnetized, this is one way to magnetize a nail, but there's not much magnetic charge here. But as soon as I turn this on, put this back on here, I have created a electromagnet. That's all there is to an electromagnet. Because what's happening here is there's a lining up of my magnetic fields. Let me turn that off. So this is called the second right-hand rule, or there is a second right-hand rule. And it says, grasp the coil with your right hand, fingers in the direction of current, and your thumb points north. So let me demonstrate that for you. Let me take that coil of wires that I had, wherever that went to. Don't know how I lose things so quick. But we can do this one. It's really odd. Must have fallen on the floor. If this is my coil of wire, what I would do is I would say which end is positive and which is negative. If this is the positive end, then my fingers are going to go this direction, and my thumb is going to be pointing north. Man, just a second. I don't know where I had a bigger coil of wire, and it's disappeared. Let me take these off so we can see it a little bit better. If I take this coil of wire, and I'm just going to make a coil out of it, like that. Not a very good coil, but I had to do that real quick, so I lost the other one. What I would do is I would say which way is current flowing. If this is positive here, then the current is going to be flowing this direction, and my thumb would point north. So this end of the coil would be the north end. If I turned the electricity around, so the electricity was flowing, this was the negative end, then my fingers would have the electricity flowing the opposite way, and my thumb would be pointing the opposite direction. And that's called the second right-hand rule. By the way, the amount of strength of that magnetic field will depend upon how much electricity. So if I have a higher current, or if I have longer wire, in other words, when I made my little electromagnet here, I put a lot of coils on. If I had put half as many coils on, I would have had half the magnetic field. If I had done 10 times more coils, I'd have 10 times the magnetic field. If I ran twice as much current through it, I would have twice as much. So with those coils, we can do all sorts of things. We're going to run out of time for this video, but one of the first applications of this was a telegraph. And if you were at school, we would actually build a telegraph. But a telegraph simply has a wire, a little nail basically, with a coil of wire, and then on top of this is a little piece of metal. And when I tap this metal down, it's connected to a wire, and those wires are connected up to another coil of wire over here, to a nail with another coil of wire that goes to it, and another piece of metal. When I tap this down, electricity starts flowing, this becomes magnetic, and this magically clicks down. So as I touch here, this clicks down. So they would sit on one side, that's where Morse code came from, and they would push down, and almost instantaneously, maybe 1,000 or 2,000 or 3,000 miles away, this side would go down. It's the first form of modern communication, and it came directly out of this idea of the magnetic field that's around a coil of wire. So what I'm going to ask you to do is, in your book, problems 5 through 9, and then 59, 60, and 64 through 66. And I know you don't have answers for some of those, but they're mostly drawing pictures and whatnot. So I'm going to have to help you with some of those. And there's a video that I want you to watch. It's a YouTube video, and it's on the right-hand rules. And that's because he's able to show you the right-hand rules much better than I'm able to show you. The other thing is, he'll go on to the third right-hand rule. Go ahead and watch it, and then the next video we'll talk about our third right-hand rule.